Oh, I see.
Maybe trying to think of global challenges.
Jerome, so I'll open the first one. Who's Jerome? What's his title? I don't see.
Wednesday morning, Villanueva. Yeah. I wonder if they're Wednesday morning.
Okay.
Yeah. On the online thing?
No, on the cafeteria.
Oh, okay.
If you need that.
This is fine. I'm just going to wait till this little clump sits down right here. It's time to sit down, Kevin. Thanks, everybody, for coming back for day 3. You never know what's going to happen, so glad there's so many smiling faces. Some of them new. Some people just arrived this morning, and probably others have left. But in any case, just a reminder that right after the morning sessions, so technically in the afternoon around 12:35, we're going to have the group photo out on the front steps. So don't disappear immediately. Give us another 5 or 10 minutes to take care of that, and then it's lunchtime. A couple notes about tomorrow night. The buses will leave here promptly at 4 to give us time to get through the awful Parkway traffic and get everybody checked into the National Academies. So you're probably not going to have much time, if any, to head back to the hotel after the closing talks. So please plan accordingly for that. It is, for NASA folks who might be curious, declared a widely attended gathering, so you can come and eat the food without putting a $10 bill in the basket. Don't worry about that. They did initially tell us that we needed to have our X cards with us, but that's no longer true. They waived that, so don't sweat that one either. And I think that's probably all I have to say this morning. So we're going to turn things over to Andrea Petrich from Space Telescope, who's our morning chair, and we'll get going. Thank you.
Thank you. Good morning, everyone. As Jason said, I'm Andrea Petric. I work at the Roman Telescope branch, and I'm very excited about this morning's session. So to start things off, we have Geronimo Villanueva.
Okay, hi everybody. So we've been hearing a lot of the great things Habitable Worlds can do, and we wanted to talk a little bit about what can be done with solar system. Typically, when telescopes are being designed by astrophysics, the main drivers are, solar system tends to be an afterthought. But in the latest telescopes, especially for example James Webb, there is a dedicated program for solar system. There is a deputy project scientist working on that, and that allowed James Webb to be very well tailored for solar system research. So the main idea of the talk is to show some of the things that you can do with solar system, and also to motivate some of the things you can tweak the technologies of the telescope so they are more applicable to you can do with solar system work. So the main thing you're wondering, we have so many spacecraft, so many things going on. Why, what have something like a Habitable Worlds Observatory can provide something, extraordinary beyond those things. But as you've been seeing from some of the media things happening already with James Webb, there's a lot of great things can be happening with something like a Habitable Worlds Observatory. And myself being a solar system astronomer, this is something that we've been dreaming about. So when we start thinking about this, it's good to put things in context. And again, this list is not far from being complete, but just to give a sense what is going to happen in the next years. So right now we have the big telescopes are Keck and BLT. We have ALMA in the interferometry side of things, and then we have coming up in the late 2020s and beginning 2030s, we have the big ELTs. And these are extremely powerful telescopes. They're going to redefine astronomy when they come up online, and they are heavily tailored, most of the cases, in the optical. So a lot of the technology being pushing on them is to do adaptive optics, things in the optical, and most of them stop at 2.5. GMT will be up to 5.3. ELT will go to 14 microns, but a lot of the first light instruments typically will stop at 2.5 microns. And then again, this is far from being a complete list of telescopes happening in the future, but just to give a sense, when we think about what are the prospects of this. And the main idea of this chart to show when are things are going to probably not be available anymore to us. So of course we have Hubble now, and you can see, well, hopefully many more years. It goes up to 1.7 microns, and the 0.1 is definitely more in the shorter range of things. Well, of course, we have now James Webb all the way to 28.5 microns, multi-tailored. It can do optical, but it's, from 0.6, but it's multi-tailored for infrared. We have Roman, which is again is more tailored for imaging, and then of course we have happening in the future. And again, this is not being complete, but just to show that by the time Habitable Worlds Observatory will come online, many of these things will not be there. And if James Webb is not there, how are we going to be doing infrared astronomy? If HST is not there, how are we going to be doing optical and UV spectroscopy? So the idea is to put this in context and also to put them in kind of a competition mode with the ground base and see where the unique niches are. And the part of the discussion is to develop, traits that we can explore when we put these instruments up there, and of course tailor for solar system work. So this is a very simple chart, but the idea of this chart is this have wavelengths here, and then here is the background brightness. So this defines, when you're looking for very faint and distant things, kind of defines what is the limiting thing will define your background source. And, you're looking for very faint things, these are your limiting things. So if we were in a place with a super cool telescope and there's nothing, you would have the red trace. As you add a 50 Kelvin telescope, you see you get this big bump here. That's why, kind of James Webb stops at 30 microns, because over there it becomes not so sensitive. Still very sensitive, but not so sensitive. In the case of ground base, just looking at the background, internal background sources in our own planet, then you have air glow that is a big source of noise in the optical, and that's why having a space telescope just by background sources, without any technological aspects, defines your sensitivity. The thing is that if you actually have a ground-based telescope, ground-based struggle with other things, and this is where it's good to compare with the ELTs and all that. The atmosphere, our own atmosphere, produces two big things. Of course, it's warm, and it produces a lot of heat by itself, but also produces a lot of absorption, absorbs a lot of the light. So it means that, when you go here, it becomes a kind of a place that you have no chance to detect anything, pretty much. There's a lot of science you can do. Solar system, some of the giant planets you can do very well in the infrared, but your target case is drops like a rock when you go here. And then, of course, here you can still get competitive a little bit on the ground base. There are some windows you can do from ground base. But of course, you can see the big niche in the ground base has been the optical, and it will probably remain the optical because it's a place where you have relatively low background. Of course, UV is out of the discussion here, and also the infrared. So based on that, this is a prelude of what is the sensitivity. So I organized the talk into 3 sections: the UV, the optical visible, and then the infrared. There are 2 talks tomorrow, one by Amanda Hendricks and another one by Kari Mand, and they will go deeper into the solar system. Actually, for ultraviolet science, Amanda is the person. So definitely I'm excited about hear her talk. So let's talk a little bit about ultraviolet science that we can do things. So these are things that, look at HST. You can study this is a JunoCam image, but also HST, you can get the UV, which is something that is, you have to be in situ to make those measurements, or you need something like HST to make some measurements. When Habitable Worlds arrives probably there, maybe Hubble will not be there. So if you want to do these things, or you want to study the evolution of these planets and the climatology and how the planets are, you need to have a facility that can make these measurements. And this is an image done with MAVEN. This is actually done with an orbiter around Mars, and it has been especially designed to be afar from Mars, so you can make these extended images. Most of the images that we get from Mars are like traces like that. You can see a little bit of a striping, because we are doing orbiting around. It's very sensitive to make mapping and very localized things, but you don't get the global picture that you will get for an observatory like Habitable Worlds Observatory. So you can study, volatiles of species. UV is powerful to study, atmospheric laws, water and volatiles, upper atmosphere, ionosphere, interaction with the solar wind. MAVEN has been designed for that, and it has a dedicated UV instrument. But again, the thing with these dedicated things, you don't get the global picture, so Hubble has been fundamental to do these things in the UV. So I just wanted to give you a sense here. This is JunoCam, 30 kilometers. You can see this beautiful. They are, appear on the news. But if you had a 50-meter, I know they ask us to dream for this talk. So I'm gonna start talking about LUVR A with 15-meter. But if you think about the resolution you can get of Jupiter, it's going to be 24 kilometers. It's actually better than JunoCam in orbit around Jupiter. So this is extraordinary you can get with something like Habitable Worlds around in the solar system. I study a lot of comets. I think, when you're looking for faint or things which are very difficult to measure, something like Borisov, this is an object that we think came from another solar system. It was flying to us. We needed to have the most sensitive techniques to make those measurements. And this is where the UV, as we've been talking about, has a lot. You can do a lot of great science and a lot of sensitivity when you do it in the UV. So, for example, it was a detection that it was done with HST and detection of CO, and you can see all the molecules. And this was a very important paper because, first of all, demonstrated the value of HST, but also how to study these objects, which there's no other way to do it. We have tried with infrared and optical, but the UV was the one that provided us the top sensitivity to make these measurements. And that was done with HST. So if in 20 years HST is not there, we need something like that in the sky. And this is just to give you a sense, some of the science you can do. One of the things that this is something done with another comet. This is Comet 67P. This is something we actually flew to the comet, been there, make those measurements of water, and study the electrons, not photons, were responsible for the water release on the surface. The interesting thing about this, we actually, again, we had to fly to the comet, and take the measurements with a UV spectrometer there to make this measurement. And it's like you can have with a Habitable Worlds Observatory like 20 of those missions pointing to every comet, and you get the same science case without actually flying to the comet. And I find that's the value, something having a general purpose observatory in the sky. Some of the wealth of the lines you can do, and again, this is, as we've been talking yesterday, how short you want to go, how red you want to go. If you are in this wavelength range, you can see some of the wealth of lines you can see in a comet. You can see you can go from water, oxygen, CO2, and all the products of these molecules. And it's a plethora of molecules. And if you have high enough resolution, you can start separating them. And again, this is done with Hisaki. It was a comet. It was kind of a bright comet. Hisaki is not extremely sensitive, but it allows to do extreme science. If you have a dedicated UV spectrometer, you can do this for even fainter objects. And you can map it. So again, if you had a comet at 1 astronomical unit from us, and we had a nucleus of 6 kilometers, the resolution with a Habitable Worlds, let's say LUVR A type, it will be 6 kilometers at the surface, which is incredible. You can actually map the coma and the molecules coming out of the comet. And you can do that for the hundreds of comets out there. So this is something that is pretty remarkable. You don't have to fly to the comet. You can just point and take the data. One of the things that has been very interesting is the icy moons. Especially these are plumes detection in Europa. In the moon Europa, we have a dedicated mission now going to Europa Clipper. And one of the drivers of this mission was the idea that there were plumes in this moon. And the measurements for those plumes came from HST. So HST is pretty much defining how we planetary scientists are defining our missions. So it's important to have, that's why general purpose observatory is very important. Yet these measurements are very challenging, and this is the value of combining, a good instrumentation with, sensitivity. In the case of Hubble, the measurements were, you can see there are these blips here, and those blips are the ones considered to be the plumes. The measurements were very, very difficult. Actually, what the measurements are for the different bands of, oxygen and hydrogen, different lines, and this is what the Hubble actually measured. So then what this team did is that they modeled the surface of the moon and then took it out and produced these residual things, which is the plume. As you see, it's very complicated. Higher resolution will be important. And this is for Europa, and I will show you more. You can actually do this in other moons. But the main idea is that a lot of the Jovian moons have similar sizes. So you can do Ganymede, Callisto, and look in all these things. And having a bigger aperture, being more sensitive, and bigger spatial resolution will allow you to map this in incredible detail. So I just want to, this is what HST did. This is the paper in 2014, which I think has been fundamental for exploration of the icy moons. It's defining how we're going to go to these moons now. And this is what a nice simulation done by Roser Juanola, which is here in the audience. And this is for, again, 15-meter telescope. You can actually start seeing now the striping on the surface. You can now see the structures of the jets coming out. And again, the problem with these jets is that they've been very elusive for people to see if they are there or not. And now you can actually see them and map them. And even if you go to a 9-meter or even shorter, you still get a lot of the structure there. So you can still do amazing science with a smaller aperture. I mean, in this case, you are looking for diffraction limited capabilities in the short wavelengths. Okay, so now let's move now to the optical. So I think this plot is kind of busy, but let me explain to you because I think this is, if you do small bodies, which is, if you ask me, is a big chunk of the planetary community, it is what makes the dramatic orders of magnitude improvement in the sensitivity. So here's a time of SNR 5 in hours to detect this body and quantify it. And this is the diameter at 40 astronomical units. This is very, very far away. So you can see the LSST, this is an old slide. It shows how if you do the dedicated observatory and make these measurements, you can actually get to these things. If you have LUBOR B and LUBOR A, you can actually go much more sensitive, orders of magnitude more sensitive, and probe at 4 astronomical units, which is the TNOs, the Kuiper Belt objects, all the confines of the solar system. You can actually map them with much shorter time and actually much more bodies. So you can use something like a survey to characterize them all, but then you can actually characterize a composition with something like LUBOR A or LUBOR B. And these are orders of magnitude more sensitivity. And I think this is a similar plot in that sense. We have changed the axis here. This is the inclination here, and this is the apparent magnitude. And again, if you look at, for example, LUBOR A, the limiting magnitude was 33, so it will actually continue all the way out of the chart here. So just focus on what we know right now based on the ground-based things. But for them, these are some of the big ones, and they look big, but they're actually very small. And you can actually characterize the atmosphere for something with, like a Habitable Worlds Observatory. Then for all these guys, you have so much sensitivity, you can start temporal and spatial variability. And for this one, 24, you can do characterization of binaries. And you actually do size distributions all the way to 1 kilometer. It's a very small primordial bodies in the last confined of the solar system. And just to give you a sense, what is this? How is this into sensitivity? So, just to give you, so this is HST now. This is a 9-meter diffraction limit pattern, and this is a 15-meter. This is what a scene you will do with a regular telescope on Earth at 0.5. A good scene, actually, in Mauna Kea. You can see, again, it will be much bigger than the whole thing here. And imagine that the planet night planet is there. I mean, this is a highly hypothetical thing. Maybe they're speculated to be at 200 astronomical units. You may be able actually to map it to get the patterns on this with something like a Habitable Worlds Observatory. And this is the important thing about what we're talking about the backgrounds. So large habitable worlds can go 4 times deeper in 10% of the time that HST requires. And it will be much more sensitive than any ALT for this kind of observation. So again, the background sources, when you're looking for faint and small bodies, is dramatic what you can do for something with this facility. I'm back now. This is the optical view of the 2 planets that we were showing before. I've been studying a lot Mars, and we try to do adaptive optics on Mars. It's not possible. Mars doesn't have bright moons next to it, so it's very difficult to lock that adaptive optics. So pretty much we always observe Mars with seeing-limited observations, which is Mars is maybe 10 arc seconds, 20 arc seconds, very occasionally. So it means that you have a bunch of pixels, but you don't get a high resolution. So having something that you can actually make the observations without having to worry about a scene is very important for things like Mars. You can do the water cycles, change with the poles, and you get the global picture that is very rarely get from orbit. Actually, you don't get this from orbit. You always, have to, this is a collage of multiple images taken from the orbiters. Climatology, dust, clouds, oxygen and ozone observations. And again, just to give you the sense, the resolution of Mars will be 2 kilometers. This is even better than orbiters around Mars now. You can get sensitivity resolutions, which is extraordinary with something like a 50-meter dish telescope. And you can also go to Mercury and Venus. I mean, right now, these are planets which are very difficult to observe. So, you can actually maybe go to maybe 0.4 astronomical for some comets. So again, having this requires some speciality in the telescope. And again, we are putting them here now. So when the telescopes are being designed and some of the considerations, keep this in mind, this science can be done there. So the niche, nevertheless, for solar system will be, for certain cases, the competition with ELT is going to be, for the optical will be brutal. I mean, ALTs will do an amazing job in this range. But there are specific things that I was showing you that I think, nevertheless, in 20 years, we have that capability will be pretty impressive. We cannot do I/O on many objects. We can do, these are some of the things you can do with ground base. And these are, so I think we have to keep that in mind when we're thinking about what ground base can do. And of course, you can have this massive, large, and you can do this standard surveys. But if you want to do high contrast, as we know very well, of exoplanets, things like that, we require, coronary star shade that it's only achievable, and that's why the optical is going to remain a big science case. But having a capability of a spectroscopy, HST capability, and a bigger aperture, as I was showing you, for solar system will be very valuable. So I'm going to go to the infrared. This is kind of I know infrared, most people think infrared stops at 1.5 microns. I'm going to try to go a little bit further out, because I am an infrared astronomer actually by nature, so I will try to go a little bit longer. And I will try to convince you that going to longer wavelengths, there is a science case there. So this is a figure that we did I know it's a busy figure, I apologize. But this is in units of wave number frequency, and if you want to, it's roughly around 3.3 microns. Again, we are going a little bit longer here in wavelength. But I just want to show, this is where all the hydrocarbons emit. And this is the prime area where all the molecules are there. So if you want to look for molecules, you need to go all the way to the 3.3 micron area. And just to show you what all the things are, you have acetylene, ACN, water, methane, OCS, formaldehyde. This is a beautiful area for doing spectroscopy. So they definitely provides access. And the challenge is that a lot of these things, I wouldn't say a challenge, but a lot of the things can be done from ground, because the 3.3 is kind of there's a lot of background from Earth. But if you ask me, ELTs will do a lot of good work. I think the niches where I think that this is something in space will be pretty noble is these ranges between 2.5 and 3 microns, which cannot be done from ground, and the 1.1, 4.6. And those 2 windows are the ones which are notable. Especially, so if I try to convince everybody to go all the way to 4.6, I'm not going to have a lot of pushback. But I will try to convince with this talk that you may want to go a little bit longer, all the way to 3 microns. I'm not saying about chronography, but I'm saying that you can keep a channel that can go all the way 3 microns, and you can do extraordinary science if you go a little bit longer in wavelength in the infrared. So this is what we did for Mars, and I want to show why do we care about all these molecules. So in the case of Mars, it's made of CO2. It shouldn't have any organics, any volatiles. So the only way you can deliver, or you can have an organic signature on a planet like that, it has been delivered by small body, you had geology happening underneath the surface, or releasing gas like methane, or you can also have the big hypothesis that underneath here you can have like a niche of maybe some sort of live bacteria producing methane as a methanogen. So the search for organic compounds, especially having the diversity of molecules like ethane, you can measure all the molecular compounds, allows you to maybe infer a little bit about the source and make those measurements. That's why the infrared makes such an important case. In the case of Mars, we're still debating about this idea, and the debate is still there because we think that there may be some subsurface aquifers. We want to make those measurements, and they are very difficult to make from ground. These measurements has been a lot of debate about the possibility that the methane is there, but a lot of the things don't see it. Actually, only the rover sees it, and some ground observation that I actually participated that we think we saw it once there. So this is what we are thinking about a place like Mars. And the signature, if you go to 3.3 microns, this is the brightest band of methane, and again, this is very small amount, 50 parts per billion, you may be able to see it. But I think the main thing is not the big, is the small bodies. Again, if you keep going in the long wavelengths, you can see all the bright molecules. If you go to shorter wavelength, this is what will look like a comet will look like. This is where the booming water features are. So if you want to detect water, you need to go all the way to 2.7. This is where water is actually. This is the prime search for water regions. If you keep going there, you get the organics. This is with James Webb. You can get the isotopes of CO. You can get, if you go all the way there, you get the other things. And you can get isotopes of CO2. But I think this band of water is the one I'm trying to convince that we should try to get in some form, in capacity. And I wanted to show this paper just came out 1 month ago. Enceladus, we've been there. We had Cassini. We were flying through Enceladus. But nevertheless, James Webb took 2 minutes of integration of Enceladus and make this plume detection on thing. And in 20 years, probably not going to have a James Webb anymore. So if you want to make those measurements, or want to make measurements like this on other moons and see if these moons are releasing any type of volatile, we need to have that 2.7 micron band. And I wanted to say, the first 2 James Webb solar papers have been about the 2.7 microns. So even though James Webb can do all the way to 30 microns, the 2.7, which is very close to Habitable Worlds, you can see it. And this is the feature in a very faint body called Main Belt Comet, and also here, we can see this in a little bump there. There are these emissions from Enceladus. Also, in this region here, we can actually study the distant bodies like TNOs and Kuiper objects. You can move from methane, water, CO2, nitrogen, and there are a lot of signatures of ices on the surface that are accessible in this area. Actually, this beautiful image you have seen of Pluto is colorized based on the infrared measurements done with the instrument there. So again, this region is very rich in ice features, and if we had access to that, it would be great. And I just did for exercise. People say, no, it's impossible, because if we go to that wavelength, we need to keep it cool. So yeah, it's true, but the question is how cool you need to make it work. So I tried here with 200 Kelvin, the same measurement we did in Enceladus, and you start see the lines. This is where the habitable worlds if we were at 200 Kelvin. And then I put 250. Of course, you get more noise, but you can still make the measurement. I went 280, still there. 300 gets a little bit iffy. So I'm saying that, even though it's difficult, you don't have to keep it at 50 Kelvin. We are saying you're at 2.7 micron for a lot of solar system work, even if you keep it at, temperature you can get. So I think some trace needs to be investigated about that. So there's a trade between telescope and, I understand that, but we should try to explore those trades. I think we need to see how the penalty will be in the UV, and, we can allow a full access to the infrared. Having a 2.5 would be great. I'm not saying about a full simple, maybe even a very simplified prism or some sort of instrument that can have access to that would be great for solar system work. And, many other things will not be available. So having that capability would be great. So, that's all. Thank you.
Perfect timing. Any questions?
I just would like to add that for extragalactic astronomy, also access to the infrared or near infrared would be important. So if there are some studies that can be done towards this goal, I think this would be great for the extragalactic
perfect.
Astronomy also.
That's great. Thank you. Thank you for sharing that. Yeah.
We have any questions online? No. Any other questions? Yes.
Great talk, Geronimo. I would expect that solar system science is going to be one of the areas that is going to drive things like the instantaneous field of regard. I was wondering if you could comment on how JWST's instantaneous field of regard has either enabled or made solar system science difficult.
Yeah, that's a great point, Chris. Look, and I have to say, when JWST actually was designed, technologically speaking, was designed without solar system in consideration. So field of regard, many other things were not there. But for example, one thing that was added was the tracking of solar system objects was added a posteriori. And field of regard, in the case of solar system, in the case of Mars, which is, you had to wait 2 years to see Mars. A lot of the outer planets, every year we can find a way because, we always don't move so fast. So pretty much, you don't have a lot of objects. Of course, you miss Venus and Mercury, but even with the field of regard considerations, you can do amazing science. I think it is a consideration, but most of the people have been involved, especially with studying small bodies. Anything, even on Mars, we can do is fine in the case of that. So, I mean, again, the case of what I like about the case of James Webb is that the James Webb team, technical team, embraced solar system and they dedicated improvements to make it happen. So I hope that with Habitable Worlds Observatory, that we are more in the initial phase. Maybe some of these tweaks on the technology can be added and they become natural of the observatory and they are not add-ons in the future.
Thank you. Any other questions? All right. Maybe while the next speaker is setting up, I was wondering, you have this fantastic multi-facilities approach, and whether you have any requirements in terms of the science infrastructure that we need to set up.
For them.
Yes.
Yes, I have not thought about it sincerely in detail, so I wouldn't know how to reply intelligently about it, but that I would not reply that.
Okay. It's complicated.
Yes. Okay, thank you.
Thank you. So now it's my great pleasure to introduce Marianne Limbach.
There we go. All right, thank you. Hi, today I'm going to be talking to you about monitoring exoplanet weather and detecting exomoons with the HabWorlds Observatory. So first off, I want to talk about what science cases could be enabled with the HabWorlds Observatory if we conduct photometric monitoring of directly imaged exoplanets. So by doing this, we should be able to measure exoplanet light curves, which means understanding their weather patterns, climate changes, rotation rates, and seasonal variations. And we should also be able to detect exomoons, including those in the habitable zone. Now, this isn't something that was discussed in great detail in the Astro 2020 report, but it turns out that these science cases are absolutely critical if we want to be able to detect biosignatures on exoplanets. So today I'm going to talk about why that is and what we need to do to be able to do this. So I'll include a discussion of the science cases enabled by precision monitoring. But first I'm going to briefly talk about what precisions we can expect with HabWorlds. So photometric monitoring with the Habitable Worlds Observatory should enable us to do a lot. And here what we're talking about is the ability to monitor changes in the broadband or white light curve of directly imaged exoplanets. So we know that our nominal contrastability requirements, so the fluctuation of those speckles, should be about 10 to the minus 11. Now, if this is the case for a terrestrial world, one that is about 2 times 10 to the minus 10, the contrast, in contrast, we should expect a precision of about 5%. So that means we can see fluctuations in that exoplanet of 5% at 1 sigma. And then for a gas giant, which is somewhat brighter, so 10 to the minus 8 contrast, perhaps we can get down to precisions that are about 1/10%. So what science can we do with this? So one thing we might want to do is monitor the weather on gas giants. So this is something we currently routinely do for free-floating planets. And we know in the infrared that we typically see amplitude variations due to weather on these worlds of about 0.5 to 3%. So if we want to be able to detect similar amplitude variations in the visible, we're going to need about 0.1% photometric precision with our HabWorlds Observatory, which is well in line with what we would expect. Now, what's interesting is that while we're integrating on terrestrial worlds, often for days at a time, we may be able to simultaneously observe the light curves of these gas giants that are in the same system without the need for additional observation time. So it's very possible that we'll get these observations essentially for free. Another thing we might want to do is monitor the weather on terrestrial worlds. So we can imagine a world that has land and oceans distributed across it. And as that world rotates, it also produces a variability signature. If that world has a large amount of land and oceans, we may see variabilities in the 10 to 20% regime, which would require a few percent photometric precision. Assuming that signal to noise is there, that should certainly be achievable with this observatory. Okay, so if we're monitoring the light curve of exoplanets, both gas giants and terrestrial worlds, we also expect to detect exomoons. So I think exomoons are going to be very important for the HabWorlds Observatory, and this is for several reasons. So first off, the 2020 decadal, of course, ranked the search for life as one of the premier science goals for the 2020s. And it turns out that moons can be habitable worlds too. And not only that, but we think the HabWorlds Observatory should be able to find some of them. Furthermore, we think that the dynamical effects of moons may be important for habitability. So we see this in our own Earth-Moon system. Our moon plays a role in the habitability of Earth. And so understanding the prevalence of moons around other terrestrial worlds may help us understand the importance for those worlds in the formation of life. So furthermore, even if we want to, we can't ignore moons. So it turns out in some cases, we expect exomoons to surpass the brightness of their host planet. So we saw this recently with the NIRCam images of Triton and Neptune. So we see Triton outshining its host planet in those blue, the blue end of the near infrared. And so if we're not including those exomoons in our modeling, and we don't know how to create those blended moon-planet SEDs, then we're not going to be prepared for these observations with the HabWorlds Observatory. So that brings us to our next point, which is in many cases, we know where to go look for these gas giants, thanks to wonderful RV surveys that have taken place over the past decades. But we don't know where the moons will be. And so by detecting these moons, we're likely to provide the first constraints on exomoon occurrence rates. So these are going to be exomoons, somewhat similar to our own solar system. These are planets that are analogous. And so we'll really get a good picture for the first time of what moons around solar system analogs look like. So we think that these exomoons should be detectable via a few methods. So that could include detecting them via transits in the light curves of exoplanets, as well as via phase curves. And we may also see them in spectral signatures. So I think the transits and phase curves are particularly key, as this allows not only for detection, but for confirmation of the exomoon. So in the case of spectral signatures, we can really run into some scary scenarios. So one of those can be a case where you get a planet-moon system, neither of which have biosignatures on their own, but combined together, their SED appears to. So you can get this scary false positive signal from a moon-planet system that looks like a habitable planet with biosignatures, but isn't. And so one reason that we want to be able to detect moons is so that we're able to find this scenario and differentiate it from our real habitable planet that does have biosignatures. And so currently we're thinking about ways to do this with the data and how we know which one of these scenarios we're looking at. Okay, so spectral signatures are hard because often we don't know if that additional flux is coming from the planet or a moon in the system. So these light curves are key to differentiating those two sources. So first, let's think about transits of moons in our light curves. So we think that transits of gas giant planets will be common. So this is for a couple of reasons. First off, we think the transit probability of exomoons analogous to Io, so those that are really close in, should be quite high. So specifically here over on the right, we see the transit probability of gas giants in our own solar system, as well as gas giants, exoplanets that are gas giants, is quite high. So it's sort of in that 10 to 20% range. So in addition to that, we also expect those close-in Io-like moons to be ubiquitous. So both theoretical models and observations in our own solar system would suggest that these close-in moons form very often. Now, coupled, if that is indeed the case, coupled with the high transit probability, we would expect 1 in 7 gas giants to host a transiting moon. So if we're observing these worlds with the HabWorlds Observatory, what do we need to be able to detect those transits? So we expect transit signatures from these moons, transit depths, in the range of about 1/10 to 1%. And if we want to detect those transits with the Habitable Worlds Observatory, we're going to need photometric precisions of about 0.02 to 0.2%. Now, as I said at the beginning of the talk, we're sort of expecting there to be 0.1% precision nominally on these gas giants. So certainly that gets us well into that Earth-sized moon regime. But we can add multiple transits together to detect smaller moons. So Ios are still certainly within reach. And if you think about it, this could really be an important method for detecting exomoons in the habitable zone. So if we want to understand the prevalence of habitable exomoons, this may be one of our best techniques for doing that. All right, and so we may also want to do this for our moon. So we can imagine an Earth-Moon analog. So can we detect that with HabWorlds? So it turns out that the transit depth of the moon around Earth in reflected light is about 15%, so it's a very large transit depth. And to detect that, we only need a few percent photometric precision, which means it should, in fact, be detectable in many cases. So the transit probability of our moon is much lower. It's only about 2%, much lower than we saw for those moons around gas giants. However, if we're looking at many, many terrestrial worlds, there's certainly still a chance that we may find some of these moon analogs, and they could be very important for us to understand the prevalence of life on those worlds. These transit durations of our moon tend to be pretty long, so our moon has a transit duration of about 4 hours. For comparison, Io is about 2. Now, the last way that we might think about detecting exomoons is via phase curves. So it happens that exomoons and exorings of Jovian-sized planets in the habitable zone and beyond should be brighter than their host planets in the near-infrared in many cases. This is because gas giants contain molecules in their atmosphere that absorb that near-infrared light, whereas the moons and rings reflect. So I showed on an earlier slide that image of Triton and Neptune, and you can see here we have a similar scenario for Jupiter and Saturn. So these are all wonderful images that NIRCam has provided us of these worlds, in where we can see that the moons are comparable brightness to their planet, and rings can outshine them as well at certain wavelengths. And so phase curves may be a way for disentangling blended moon-planet SEDs. So we can imagine a scenario where we have a somewhat self-luminous planet in the infrared, the near-infrared, and then a highly reflective moon. Now, as that planet-moon system orbits its star, we're going to get a strong phase curve from the moon, whereas we'll see less variation from the planet. And using this information, we could potentially disentangle those two SEDs. And so to do this, if our moon is indeed comparable brightness to the planet at these wavelengths, we may only need a photometric precision of about 10%. But unlike the other cases that we've been thinking about in this talk, here you need to maintain that 10% stability over the course of years. So you need to be able to go back and visit this system and build up a phase curve of that planet-moon system as it orbits its star. And to do that, you have to be able to have an observatory that can really reproduce that precision as it comes back to visit that system. So this is a very unique requirement that we might want to keep in mind as we're building our observatory. So another thing I want to emphasize is that there is some thought that's gone into this in the literature, but not that much. And so as we move forward, we really need to work on building up more models of blended planet-moon ring SEDs so that we're prepared for these observations. And we also need to work on that light curve modeling so we understand what those light curves are going to look like of these systems. So here are my conclusions. I want to emphasize that precision photometric monitoring with our HabWorlds Observatory has the ability to enable transformative science. So this could mean the ability to measure weather patterns on planets, as well as that ability to detect exomoons, including those in the habitable zone. Now, the key to doing this science is that ability to monitor that white light curve. And if we want to do that, what we really need is an absolute photometric calibration source. So we can perhaps do this by monitoring the starlight within the AO cameras and use that as a photometric cal. We can perhaps think about something similar to those satellite spots we see in ground-based high contrast imaging. But we need that ability if we want to do these science cases well. So here in this table, I sort of summarized those science cases I discussed today, as well as the approximate requirements I think we need to achieve each one, which should be in the range of what's doable with habitable worlds. And that's all.
Thank you very much. We have time for one or two questions while the next speaker sets up. There's a question online.
Yeah, there's a couple of questions online. And the first one is from Abby, who says, what has Kepler told us about the frequency of exomoons around Jovians?
So Kepler was able to put some constraints on the occurrence rates of exomoons around planets within 1 AU of their star. So those very close in planets, we know that there are not Earth-class moons around them. Now, as we move out, sort of 1 AU is sort of pushing it. So into that habitable zone, we really start to not know what the occurrence rate looks like. And so it's certainly, we don't expect moons to form extremely close to their star because they're not dynamically stable. But as we move further out, they should start forming. And so sort of in that 1 to 2 AU range is where we would expect that to begin to occur. And we don't really have information in that regime. And it is also possible that that habitable zone for exomoons extends well beyond what would be considered the conventional habitable zone, as you can get very strong tidal heating from your planet on the moon, which can enable habitable temperatures beyond that conventional habitable zone. And so I think it's important, so we really don't have those constraints that we need for the habitable zone and beyond, yeah.
Hi, Marianne. Great talk over here. So I was really concerned about the moon contamination that you showed. And I imagine this is going to be a tricky question to answer, but has anyone done any sort of simulation work to understand the types of moons that form around different types of planets? Like, is a methane-dominated moon likely to occur around something like Earth, or is that more likely to happen around a gas giant?
Yeah, so what's really interesting, I think there was a recent Nature paper on this within the last year, is once you get down to those terrestrial worlds, you do expect those impact events, which formed our moon, to occur with some frequency. And we think those are the mechanism for forming these moons. So you can imagine if you're getting those events that form equal mass moons, or equal mass, like binary planets, then you could get this scenario where both have an atmosphere and are sort of both Earth mass worlds. So of course, all of that thought is theoretical. There's obviously no constraints on the occurrence rates of that type of objects. So certainly that's maybe something we can think about getting from Habitable Worlds, but yeah, there's not that much work that has been put into that, although there is, a little bit of literature.
Yeah, and so our next speaker is Jamie Krause. If you have additional questions, please put them on Slack as well as talking to Marianne in person.
Does this microphone work fine? Can you all hear me? Okay, cool. I'll do that. Hi, everybody. My name is Jamie Krause. I'm a second-year PhD student at the University of Maryland, College Park, and I'm also doing research with my team locally at NASA Goddard. Many of us have already seen this slide a few times, probably. First at the AAS back in January, and then earlier this week a handful of times too. This is Mark Clampin's slide, and I think Julie also had a version of it in her talk earlier. But I just wanted to show it again to remind us all why we're here. Just coming together to collaborate on the response to the decadal. And the work that my team and I are doing, or that we're hoping to address, is all in the context of how we can optimize our search for life with the HWO coronagraph. And that comes with a lot of challenges. Optimizing our search for life is difficult. With a coronagraph specifically, we're not going to get the full spectrum. We're only going to get pieces of the spectrum. So how do we optimize and maximize our confidence for life detection while minimizing our total number of observations? And we can start to think about this by looking at some really beautiful images of spectra. You all probably recognize this. It's from the decadal, figure 1.1. I'm going to be focusing on modern Earth for the purpose of this talk. So we're not going to get this beautiful spectrum, not the full thing. It would take multiple observations to get this. We'd actually probably first observe something like this. We see the water signature and potentially our first biosignature, oxygen. Oxygen is the canonical biosignature of modern Earth, but there are numerous false positive mechanisms to make oxygen, which we just heard a lot about. So we know that oxygen alone is not going to be sufficient in letting us know if there's life on this world if we're only looking at one observation, right? So we need more than one. And maybe our second observation looks something like this, and we see methane. And all of the oxygen false positives currently known on Earth can be ruled out by methane. But unfortunately for modern Earth, around the sun, methane's spectral feature is extremely weak and difficult to detect. But thankfully, the detectability of any gas, including oxygen and methane, depend on photochemistry. And while Earth might be more than one planet, when you take that into consideration with different dimensions of time and different eras of Earth, you can learn a lot through photochemistry, which goes back to a repeating lesson that we all know in astrobiology, which is know thy star, know thy planet. And it really emphasizes how badly we need to get UV characterization of these host stars. And HabWorlds is thankfully meant to be capable of doing something like this, if not simultaneously, then in near real time with the observations done by the coronagraph, which means we all need to just start understanding this in a lot greater detail. So that leads me to what I've been working on, the specific questions that this study is trying to answer is mainly just like, do biosignature gas pairs work for HabWorlds? Specifically oxygen and methane for modern day Earth, and how do those biosignature gas pairs change as a function of stellar type? So to do this, we set up a 1D model called Atmos, and it's a coupled photochemistry and climate model. We've had a lot of recent updates with this model over the last couple of years. And it's important to highlight those significant improvements to the Atmos code since Jada Arney's 2019 study. So these recent updates include an expansion of the chemical reaction rate networks for Archean and modern Earth analogs with updated chemical reaction rates and improvements to the photolysis cross-sections and quantum yields of that code. And I want to just give a quick shout out to Sandra Vasselberger for championing these efforts. So this model allows us to look at different star-planet interactions by looking at modern-day Earth around different star types and starting to compare what we might see in an atmosphere if we're looking at not just our sun, but different stars like FGKM, So I recognize that depending on everyone's background here, these plots might have some jargon on them. So I want to explain what we're looking at for a second. These plots are 3D logarithmic contour plots with the y-axis being oxygen mixing ratio. And by oxygen mixing ratio, what I really mean is just the fraction of the atmosphere that's composed of oxygen. The x-axis is the methane flux. And then the color bar axis on the z-axis is the methane mixing ratio, or the fraction of the atmosphere that's composed of methane. So now that we have all that covered, our results were compared to Jada's 2019 study, and they were found to be consistent. So that's really great that the model updates are working well. So it validated past results from our team, and then it allowed us to expand it to different star types. So this is the sun and an M-type star. And we also looked at an expansion of different K-type stars. So these are the same axes that I just described a moment ago, but this here is the sun and a K2.5 star. So it's kind of hard to distinguish between both these plots, but when you get into later type stars, we see more methane being present in like a K6b star, which is good for HabWorlds. And all of this is setting up the foundation for how to optimize the search for life, right? So our team has been building this biosignature decision tree, and this is the current version of that tree. This is just a current work in progress, but this version of it has been submitted. Amber Young on our team submitted it last week, so that's exciting. But we're still thinking about this in the context of all these different star types. So this is based on the LUVAR study report, and I could spend an entire hour explaining what all of the colors mean and all of the observation chronograph bandpasses we would need to get to something like these end-member cases. But just really quickly, I'll try to point out that we're gonna, like, the entire goal of this decision tree is to sort these different types of planets that we're gonna be looking at into 3 main categories. So the first one being inhabited planets, the second one being worlds without global surface biospheres, and then the third one being more ambiguous cases. And so just real quick, circling back to those questions I showed earlier, I just want to leave you with some key takeaways. Do biosignature gas pairs work? Yes, they do. They allow us to step through the decision tree with a minimum number of observations. This is really exciting because we can look for biosignatures and rule out false positives. And we can also look for the first detectable gas in an atmosphere and then look for its corresponding gas pair. Investigating biosignature gas pairs is really useful due to their ability to help discriminate between biotic and abiotic gas sources. And it also allows us to build these decision trees that help us optimize our search for life. And then I didn't have time to go into all of our key and plots just for the sake of 12 minutes of speaking, but I'd be happy to show you all how these biosignature gas pairs change as a function of star type for those types of worlds as well in the question section.
Thank you. Any questions online? Yes.
Jamie, great talk. Mark Postman, Space Telescope Science Institute. How important is simultaneous UV observation of the host star when you're making these biosignature observations?
How important? I don't know how to quantify that for you. It's a really good question. I think it's really important, but maybe someone else here in the room that is a UV expert would be more able to answer that. I can think about it too a little bit and then talk to you after.
Eric Memajek, XUP and JPL. You emphasize the oxygen and the methane in those two, in the visible band and the near IR band, but I thought the strategy was to go after water first, which you mentioned in one of your last slides. How much information can you get in that narrow water band besides the water that factors into the first part of your decision tree before that oxygen and methane features that you're going after? Like, here you go. You have it at 0.81 to 0.97. So do you just want to talk a little bit more about that, what you can get, information you can get in that band besides the water?
Yeah.
I thought that's the one that would be observed first.
Yeah, so that's the hope, right? Is that's going to be observed first. But with just the water signal, like, we can't just confirm that that's life on that planet. So can you repeat, or Aki, I guess if you.
Is there other information in that band? Like, you have CH4 greater than 1. Can you so you have some information on methane in that band? Is there any other features in that band that are useful?
This would be a great question for my teammate Amber, who did a bunch of retrievals on this work, explaining like the use of this decision tree. I don't have any of her plots in in my slide deck that Jada, who mentors both of us, probably be more appropriate to answer this.
Yeah, so that's a great question and great job, Jamie. So that first scan there, you could detect methane in it if you had a Archean-like amount of methane, so much higher than modern Earth-like levels. So in that first observation, right, it's being targeted at the water band, but if you're lucky, you might also get methane if, you know, if your planet surreptitiously happens to be an Archean-like planet. If you don't see the methane, right, then you might assume it's a more modern Earth-like planet, and so then you might try to go after O2. It's also possible you could get the O2 simultaneously if it's in a different coronagraph than that initial water observation. So right here, the sort of green color is assuming they're in the same visible coronagraph, but right, like we don't know where those channels are actually going to be split. So Jamie's focusing in on the biosignature search. So in particular, she's focused on this talk, particularly on the modern Earth biosignature search, although she's also looked at Archean as well.
Yeah, I guess to emphasize what Jada was just saying, the lack of methane in that, like if you were to go to the left, you know, would sorry, just lost my train of thought. Yeah, basically it would help us rule out the ability to like confirm life in that observation. So we wouldn't be able to get high enough detectable methane abundances, and that would kind of rule out that option for us. Hey, thanks. Yep. Yeah. Yeah. Well, is it right? That's a great question. I hope so. Yeah. Yeah. So I guess the context of the ranking here is just that the K-dwarf is going to have the highest level of methane concentrations, right? So it's going to make our jobs a little easier when we see that in that observation, which is exciting, and maybe will help us optimize our observational sequence, I guess, our decisions we make with these different host stars nearby.
For a very, what? So next we have the pleasure of Claudia Scarlata.
Okay. Right. We are going out of the solar system, out of the galaxy, in a universe far, far, far away now. Okay? So bear with me. We are going to talk about another science case that I think will benefit from having a 6 to 10 meter telescope in space. And specifically, I'd like to convince you that we really want this telescope to study the reionization history of the universe and really make one measurement, which is the escape fraction of radiation, of ionizing radiation from galaxies. If you looked at the schedule, you may have seen I was supposed to talk about outflows, but outflows were really covered already, so I decided to change that. The reason I think they invited me to talk about outflows was because last time I was here for the May Symposium, I concluded my presentation on outflows with this slide that said, I really want a MUSE spectrograph, so a 1 arc-minute IFU spectrograph that covers the wavelength range of COS with the same spectral resolution on LUVOIR. Okay, so I think that was ambitious, so they decided I was a good speaker for these conferences. Anyway, I haven't changed my mind. I'm still, you will see, oops, sorry, going back and forth. I'm still going to argue for this, but just with a different science case. Okay, I'll try to take it easy. If I have too much jargon here, please interrupt me, don't be shy. So what are we going to talk about? You've seen this slide before at this conference. This is just a cartoon of the history of the universe, the way we understand it. You can see the CMB on the left, and let me just check what the... okay, this was wrong. Obviously. What did I do? I pressed this button.
Maybe stick with the
okay. Is there no? But is there a thing?
Maybe just stick with this.
Okay. That's what I was looking for. That's what I was looking for. Okay. Restart. This is the history of the universe. We see B on the side, and we are here now. What I'm going to talk about is the cosmic reionization. So this is about a billion years of time between, as I said, the recombination. So when electrons recombined with protons and the intergalactic hydrogen, the intergalactic medium was completely neutral, and a period that we see today when we look out into quasar absorption lines and so on, and we realize that the universe today is fully reionized. So something in between during this cosmic reionization, starting from the formation of the first stars, has produced this ionizing radiation that reionized the intergalactic medium. And we call this period cosmic reionization, if I haven't said that already 5 times. So universe is ionized by photons that have energy greater than 13.6 electron volts. We all know that. They have a wavelength below 912 angstroms, so in the far UV. And I will refer to those in the next 30 minutes or so as Lyman continuum photon, ionizing photon, and more. So there are still quite a few mysteries about this phase of the universe, okay? It's a very important phase. The entire universe changed, and yet we really don't have all the answers, okay? We do have some constraints. Well, we have many constraints. I'd like to show these 2 examples here. They are completely independent constraints. On the left-hand side, you see the fraction of free electrons as a function of redshift, as measured by the Planck collaboration in one of the recent paper by measuring the Thomson scattering optical depth to CMB photons. And on the right-hand side, you see now the neutral hydrogen fraction as a function of redshift and how it changes with time. And this is using many different measurements that are sensitive to the presence of neutral gas in this example. So these are Lyman alpha forest, quasar absorption lines, and so on. These 2 constraints are complementary to each other. One probes, the one on the left, my left probed the ionized gas. The one on the right probes the neutral gas. And yet you can see they both indicate a fast, relatively fast, just a few 100 million years, and late reionization, and they agree with each other. Now, the problem or the limitation of these kind of measurements is that they are global measurements, right? They just tell us something about the entire universe and how it changed as a function of time. And so really doesn't tell us much about what really are the sources that produce these ionizing photons, and don't tell us about, for example, the spatial progression of the reionization. So these things are actually important because, as we can see here, whether, for example, it is a faint source or a bright source that dominated the production of ionizing photons, it makes a big difference. So what are we looking at here? These are results of numerical simulation by McQueen et al. Some 15 years ago. And in the row indicates different redshifts. So this is time that progresses from top to bottom, from early on to closer to today. And different columns show different sources that ionized the same underlying density of neutral gas. So the neutral gas density is the same in these 4 columns, but these 4 different kind of sources that are responsible for the reionization. So faint sources on the left and progressively brighter sources on the right. And as you can see that the rarer, the brighter, the rarer the sources, the larger and kind of more spherical the ionized bubble around these sources are. And you can also see how the reionization, or the time at which the largest fraction of the universe is ionized, is faster when we have brighter sources, even though this is counterintuitive because brighter sources form later in our understanding of how structures form. A related issue is whether these ionized photons are produced by stars or by accreting supermassive black holes. We have seen in the talk from Rebecca yesterday that supermassive black holes are already common early on in the universe. And I don't know why there is this S down there. Whether I had to switch my presentation from Keynote to PowerPoint, so you get this. Right. Whether quasars or star-forming galaxies produce these ionizing photons makes a difference because of the hardness of the ionized spectrum. Harder photons would penetrate farther and create bubbles that are larger. So the reason why we really don't know yet what kind of sources, bright, faint, quasars, star-forming, it's because we're really, these constraints I showed you earlier are really global. And so they depend on the production rate of ionizing photons per unit volume. But really what we need to place those curves in the figures I showed are average constraints over the volume. So we do, when we compute those models, we look at the intergalactic medium ionized fraction, and we basically do a balance of photoionization and recombination like your H2, classic H2 regions you learned in graduate school. Again, this is supposed to be an ion. We're going to get this a lot. Okay, so an ion, which is the production rate of ionizing photons, can be written as the product of 3 terms. So really that's the only thing, the product of the 3 terms that those global models constrain. And what are these 3 terms? They are the production efficiency of ionizing photons. So this is given a given source, how effective that source is in ionizing, in producing ionizing photons. And this is normalized to the 1500 angstrom luminosity, so the luminosity that is non-ionizing. Then we have the density of the luminosity density at 1500 angstrom. And so you see the product of those two just basically gives me a number of photons per megaparsec cube. And then we have this holy grail of the reionization, which is the escape fraction of ionizing radiation, which is what I'm going to talk basically about for the rest of my talk. This is how much ionized radiation, which is produced inside the sources, is able to actually reach the intergalactic medium. Right. So far, in the models that I've described, these values here are given as constant. The luminosity density can be computed integrating the UV luminosity function. The production efficiency, as I said, is assumed as a characteristic numbers. But now, I think, again, Rebecca gave me the best setup for today. We can measure all these quantities, the green and the blue at least, at the epoch, during the epoch of reionization. So we can, for example, push the measurement of the luminosity function, so we can characterize the number of objects per unit volume, per unit magnitude, out to redshift 12. This is even before the time our previous constraints told us that the reionization started. And so now with JWST, when I presented this slide a few years ago, I would say, oh, we will measure the luminosity function, but now we are really there. Xion, the efficiency of ionizing radiation, we are in the same spot. Now with JWST, we can measure rest frame optical and UV lines out to very high redshift. So in this figure, you see this parameter, Xion, as a function of the UV luminosity of galaxies, and the color points are all sources at redshift greater than 7.5. So again, we are making this measurement during the reionization epoch, so when the action is happening. And what else, I mean, what we can also do now is to link Xion to the UV luminosity and to the number of galaxies that we have at that particular luminosity, so that we can really go beyond just a global number and we can make a measurement that is galaxy specific. However, we also have this parameter, f-escape, and you will see that f-escape is actually a more complex number, and we cannot measure it during the reionization epoch. So let's see why. I have my cartoon. It's my turn to have the cartoon here. This is a galaxy. This is a galaxy that is forming, that has many young stars. And young stars are very efficient producers of ionizing photons. This is its typical spectrum, and this is the intrinsic spectrum as the star produces it, okay? So there is an intrinsic non-ionizing, there is a non-ionizing portion of the spectrum, and then there is a break, which is just due to the absorption within the star itself and at the Lyman continuum. And you can see that the break is actually substantial. The Lyman continuum portion of this object is, depending on the particular age of the stars and metallicity and so on, 3 to 10 times fainter than the intrinsic radiation. So this already would make the measurement challenging, but this is not all. Of course, stars are actually embedded in their birth clouds. There is the ISM from the galaxy, and also this gas then attenuates the Lyman continuum radiation, of course also the intrinsic radiation, but we are focusing here on the below 912 angstrom. And the effect of the ISM can be substantial. It can attenuate now, it can further attenuate the intrinsic ionizing radiation by factor of up to 20, okay? So again, everything suppresses the Lyman continuum. When what we want to measure, the number we want, is the ratio between the escape ionizing radiation over the intrinsic one. So the blue over the intrinsic one. And ideally, we really need this measurement at redshift 6, at redshift 7, at redshift 8 to probe the reionization history and the production rate of ionizing photons. But we cannot do that. Why can't we do that? Well, because when we place a galaxy at a cosmological distance, then what happens? There is the intergalactic medium between me and the galaxy. So even if there were photons that were able to escape from the galaxy, now they would be absorbed by the neutral gas that would surround them. And so the attenuation, the measured, even if there was radiation that could escape through the intergalactic medium, I would still have to correct it by this attenuation by the intergalactic medium. So a little bit more in detail, you can see here how the average transmission of the intergalactic medium changes as a function of redshift, and you can see how this transmission drops very quickly. So basically it is prohibitive to look at ionizing radiation and make this measurement out to redshift greater than, for redshift greater than 6 or so, 5 or so. And so most studies have focused on measuring it at redshift below 4. The other thing you can see from this figure is that there is a large scatter in the measurement. So at any given redshift, if you have a galaxy along one line of sight, you really don't know how much your intergalactic medium is contributing to the attenuation. So you really want to push this measurement at a low ratio as possible to minimize this uncertainty. And finally, if you have a galaxy at higher redshift, you have a much higher chances of having interlopers along the line of sight. So the radiation that you're measuring below 912 may in fact be coming from an object that is by chance aligned with your sources. So that's why we have so far focused mostly on redshift sources, on sources at redshift smaller than 4. And we have used Hubble either for the direct measurement, when 912 is still in the ultraviolet and we require space-based observations, or because we need to measure and we need to rule out interlopers along the line of sight. So the other important point that I need to make is that because we are making this measurement at lower redshift, we need to verify that the assumption of extrapolating what we learn to high redshift is correct. And so we really need to understand what are the mechanisms that allow this ionized radiation to escape from galaxies. And these two are the reasons why we now need a 6-meter or 10-meter telescope in space. Right, so it's not like we have been sitting and not doing anything over the past years. So there was a huge investment of time, hundreds and hundreds of orbits of Hubble, hours of ground-based telescopes. And until very recently, we had very few convincing detection of ionizing radiation. So I'm going to show a few examples of empty images as spectra, which is something that was very common until recently. So this is one example. This is when we use the solar blind channel prism little spectroscopy to try and measure the ionized radiation from this galaxy here. This is an image. And you can see the 1500 non-ionizing radiation here, then the Lyman limit, then 0, okay, nothing. Well, this was, we were unlucky. Then we went and tried with imaging. Again, non-ionizing radiation here, ionizing radiation there, nothing. Here we used, again, SPC now, but in imaging. Then we pushed a little higher redshift, Wi-Fi camera 3, near UV, for galaxy redshift 2.5. Nothing. This was very common. It was a frustrating field for a while, okay? It was. And this is just a summary back in 2020, where you see that the majority, we tried to hide them, but they're gray. You can see that there's just upper limits. This is the escape fraction of ionizing radiation as a function of UV luminosity. And there were very few detections at redshift, very local redshift up to 0.4 or so, where we really minimized all the uncertainties. Now, the situation changed around that time when a few galaxies, they are on this plot, isotopes, these are called green P galaxies. These are highly ionized compact sources. When these were discovered, they had high escape fraction. So we were all excited. We got many, sorry, completely scrambled. We got 134 hours of Hubble to follow up a sample, a large sample of galaxies that we thought could be strong emitters. They span a broad range of properties, in their physical properties, and in fact, we got many detections. So the important figure is right here. You see a spectrum again, and you see a lot of signal. That's a lot of signal for us, below 912. So over the course of maybe 5 years or so, that's why I decided to change my presentation, we went from having 10 galaxies detected to 50 galaxies detected in Lyman continuum out of a sample of about 100 that are in the archive overall. So now we are really in the position to compute statistics, understand correlations and so on, and move forward. This is not making, I'm not giving any credit to Sophia Fleury. She wrote 2 wonderful papers describing this survey and just highlighting a couple of results to give you an idea. This is the Lyman continuum detection fraction as a function of various galaxy properties, how highly ionized is the gas, the age of the burst, the UV continuum, and so on. The bottom line is that sources now that we think have a high escape fraction are highly ionized. They have concentrated star formation rate and are typically very young. Now you may notice that there is a large scatter here. for a given quantities. And this suggests that Lyman continuum emitters cannot be described by a very simple model. You need a little more. And this is, in fact, confirmed by what we know from numerical simulation. This is an example of an hydrodynamical simulation of one galaxy. So this is just an L-star galaxy. And you can see these are 3 regions highlighted in this galaxy. 2 of them are not leaking, and 1 of them is a leaker Lyman continuum. And if you zoom in, we can look now at more in detail in this area. You see there is a shell of much denser gas, and colors here indicate the stellar age. So you see there are older stars toward the interior of the shell and younger stars toward the edge of the shell. And when you look at the escape fraction along the direction of those stars, you see that the high escape fraction happens where the gas has already been removed, and it's associated with the older stars because it's when there was time to remove the gas from the line of sight. So now, assuming that we can use what we learned at redshift 0 to interpret the reionization history, what we can do is to use those constraints to compute the neutral hydrogen volume density. So this has been done. These are just 2 examples of 2 very recent papers this year, one by Trebich et al., who shows the cumulative ionizing emissivity of galaxies at redshift from 4 to 10 as a function of the UV luminosity. And this is instead an example in which Lin et al. Showed also compute the contribution of young stars, low luminosity galaxies to reionization. The bottom line of these 2 papers is the same, that more than 50% of the total ionizing emissivity of the total number of ionizing photons that I need to reionize the universe is produced by galaxies that are fainter than minus 16 UV magnitude. Now, do you see the problem here? The colors in this figure on the right, these white dots and black dots, shows the data that we are using to measure the escape fraction in redshift 0. They only extend out barely to minus 18. And yet we are saying that the universe was ionized by galaxies that were fainter than minus 16. So it's a total extrapolation, total BS. I mean, not quite. Obviously, I wrote at least one of these 2 papers, so I don't believe it's total BS, but we're making big extrapolations, and this can have a large effect. So we kind of looked at it here. We extrapolated in 3 different ways on this side, and you see the effect on the evolution of the ionized fraction. The blue, red, and green correspond to these 3 curves. Okay, so what do we need to do then? We need to push to high redshift, right? Again, we need to measure this little flux, not to high redshift. We need to push the measurement to lower luminosities. This is, again, the escape fraction is a function of 1500. These are the measurements we have so far. We really need to push out to minus 14, ideally even fainter than that. And so, of course, my PhD student and I were very excited. We wanted to write an HabWorld proposal to do that, but it took the age of the universe to do it, so we decided to give up. But this is when we need HWO, right? I did some calculation with the exposure time. If we consider a galaxy at redshift 0.2, Lyman continuum would be detected, would be shifted to 1100 angstrom, and I looked at how to reach a signal to noise of 5 with a resolution of 500 over a 20 angstrom wavelength range, and we need about 40 hours per object. It's a lot of time, but it's not crazy. We need high multiplexing, right, to be able to make this measurement, to make a survey that would give us something interesting. And so, again, I would argue for large field of view because the source density in the sky of this kind of galaxies is very low. So I see I only have 10 seconds left. So I'm only going to show this movie. So what's the point now? Say that you have gone out with HWO and you have really measured my galaxies and the escape fraction. we still need to make this extrapolation between local universe and the high-end universe, right? So we saw how feedback from supernova creates this bubble. In fact, also depending on how you look at the galaxy makes a difference. What direction with respect to these outflows? What kind of density velocity field you have? And so what we really need is to probe the ultraviolet, get absorption line spectra, some of them are shown here, and look at how what the spectral features are telling us about these outflows, about the geometries of these outflows. And this little movie here showed how the spectrum changed as a function of the direction, for example, the direction of the outflow. This is what we may expect from a leaking region. We may expect to see not opaque absorption lines, while we would expect to see much stronger absorption lines from not leaking region. And of course, ideally, we really would like to do it on a galaxy in multiple positions. Again, this is ultraviolet. So we need a high spectral resolution for this kind of measurement, at least 10,000. These are two spectra of the same object observed with the low resolution COS spectrograph and the high and the medium resolution COS spectrograph, and you can see the difference. This is the same galaxy. So we don't, and the curve are different models for the outflow. So we don't constrain anything with low resolution. So again, we need high spectral resolution, possibly multiplexing for this kind of measurement. So I'm just leaving you with my summary. I presented another case that would benefit from the addition of a 10 6-meter telescope in sky. I would argue that we need a capability for multi-object spectroscopy, high and low resolution, and large field of view. Thank you.
Thank you. Any questions online?
Hi, Claudia. Fantastic talk. So my question was related to this last point that you had about, we either need multi-object spectrograph or an IFU. So,
I didn't say or. I would and.
Okay, what I mean is you started off making the case that, this telescope, you would like to see an IFU. Mm-hmm. And my question was about
a Muse IFU, 1 Archimedes square.
Okay, so is there, would you have a strong preference for one or the other, and what would be your, reason for choosing an IFU, or can the same thing just be done with a multi-object spectrograph?
Okay, so a multi-object spectrograph constructed like NIRSPEC with the shuttle can be then used to create, if you want, an IFU in a clever way. It takes time, though. I would argue that possibly the best for me would be having many IFUs that are deployable over a large field of view. So kind of giraffe, I think, on VLT, but that may be too much.
Thanks, Claudia. Really nice talk. I guess the big question in my mind is whether any galaxies in the local universe that would be accessible, even with HWO, have conditions in the ISM that are similar to galaxies in EOR. So in order, to apply those results to reionization, we'd have to convince ourselves that we could find true analogs. So how do you think we should go about that?
That is absolutely a fair question. And I haven't had time to show it, but what we are also doing is studying the escape fraction as a function of redshift out to where it's measurable. And we're looking at how it evolves with the properties of galaxies that we do know evolve. And we can do this, between redshift 0 and 4, and that's most of the age of the universe, and we can then extrapolate. We do have indication from early spectroscopy with JWST that the conditions that we are seeing are similar to those conditions in the green piece, for example, where there are these there's highly ionized gas, low metallicity. So there is some clues of that, yeah.
Nothing online.
Hi, Claudia.
Your figure in the talk.
Very nice stuff. Steve McAllis, Johns Hopkins. I was wondering if I guess, discovery of the large number of very heavy galaxies by James Webb is somehow changing the paradigm of reionization in terms shifting it away from smaller objects to the oligarchs, as Naidu calls them.
Right, I don't think so. The figure I showed, I don't remember what Maxime used on the left. I'm certain of what we used on the right. We used the new luminosity function, so with the number of bright galaxies that we are seeing. And yet we are still requiring most of the photons produced by fainter galaxies. It's really an interplay between these two parameters, the escape fraction and how many galaxies you have. So with the constraint we have locally now for the escape fraction, it's still required that we have to extrapolate to very faint magnitude to be able to realize the universe.
And let's thank all our speakers for the session.